Good. Welcome back. This is part of a series of films on or videos on using the IESve building performance tool or program, and we are busy unpacking the use of the building template manager. Now, remember, the building template manager is an important aspect of this whole assessment or analysis that you'll be doing because your geometry doesn't carry much information. The rest is really all integrated into the building template manager and where that then gets applied to the spaces themselves. So you take quite a bit of time setting up your building template manager, and then from there you'd simply apply it to the spaces and it should be quite quick. Up to now, we've discussed the use of profiles that talks about how spaces gets used and occupied. We spoke about the system that we use to define it. We've also spoken about the use of that in terms of the space conditions where we start defining the air conditioning systems that will be used when it switches on and off and so forth. The next factor that we will be discussing now are the internal gains. Now, this is how to understand this is that most of the buildings actually gets affected by thermal gains within buildings. It certainly also has electricity or energy use impact. So the computer I switch on therefore uses both energy, which is important if I want to do an energy analysis, but it also generates thermal energy to a certain degree. That also has implications in terms of the energy use of the air conditioner or thermal comfort within the building. And similarly, we'll be seeing the same happening for building users. So again, you're in your building template manager and you've now clicked on internal gains. And as you can see, none are at the moment defined for any of the spaces. Remember, we're working with the template called Office 1. That's the template that we're preparing for this, this model. And you can then click on Edit Internal Gains. Now let me just click on that again so you can see it's Edit Internal Gains. And in here, you can now start defining the various types of internal gains there are. And there are a number. I mean, it's from motors, processors, refrigerators, data center equipment, which do generate lots of energy, display lighting, task lighting. And you're welcome to look at all of them. I personally don't think it's as critical for architects, interior architects to define all of that. I think generally we in an office building, well, it all depends on what you're doing. If you're designing a kitchen or working with a kitchen, you might actually want to, in the cooking zone, define a cooking gain there, and you'll have to go and look at what that components are or what the typical thermal gains of a kitchen would be. And similarly, you will be doing the same for equipment. I generally put if you define an office, for instance, you can simply just simply use on a computer. So there's not really an energy or plug load density defined here, but and so it's called new computers. But you can change that definition now to plug load density, for instance. And I like to use plug load density because it talks about anything that gets plugged in the process. So you can fill it in like that. I'll still keep it under computer so I can find it again. And we say, do we assign it to templates? Yes, we're going to assign it to this current template. And then you can say, okay, what would be the gains that we need to define here? It's in watts per square meter. I would suggest you go for watts per square meter and not watts, because what will then be that you'll have to define each and every one of it. Now, watts per square meter means we can get a general wattage per square meter and then say, okay, that's defined for each across the board. So in the South African context and often internationally, we use 15 watts per square meter as a good basis from which to consider energy power or the power consumption of of equipment in an office. But if you are documenting an existing building and you actually know what is being used, or you're planning closely with clients and a building where you then can actually work accurately, and you can say, wait a minute, we're not going to use 15 watts per square meter, we're going to use 7.5. Then you're welcome to put that in. What you can then do is you can see there we define the meter, electricity meter that runs on it, and it's there again. It's really if you have multiple meters, like we're not going to run it on anthracite, for instance. It's not going to work. But generally, we keep all that on the same meter because we want to calculate all of that together. The variation profile again talks here about how it's used. Now, if it's equipment, then I think the office occupancy can work. You can use annual or weekly, whichever one works best. Then what you can define, and this is not necessary, I often don't necessarily define it, but you can decide that, you know what, I am going to assume that 100% of the energy used gets translated into sensible heat gain. That's not really accurate. I think not, especially not for equipment, because certainly the laptop that you use don't generate as much heat as the amount of electricity it uses. But if you are designing a kitchen, for instance, you might actually start saying, okay, wait a minute, there's quite a lot of heat generated. I might actually want to adjust that in the end. If you're working with lighting, so if we go, for instance, for general lighting, and you say, okay, wait a minute, let's add general lighting, and we can just call that office lighting. There, I would say you can actually say, and office lighting generally is about 12 watts per square meter. It's again a good assumption. And you can say, let's assume that 100% of that actually translates to heat. It's not quite accurate. I mean, it all depends on the type of lamps you use, but lamps do generate lots of heat. So it won't be inaccurate to do that. And again, you can adjust that the use, saying it's only when people are there. And if you really wanted to, you can also say there's a dimming profile that happens. So the dimming profile will then say at the mornings it will 0.5, and then it will run to 0.75 in the day, and then maybe you wouldn't like that, which argues that there's less light being used. Again, that's a profile you have to prep, and then you can put it in. Similarly, if you use people, because that's important, we would then say, okay, let's add people. There we go, and we might call them office people. And we say, well, we want to assign that to our template again. Again, we look at our input mode. We look at square meter per person. So how many square meters do we actually allow per person? And you'll see that, for instance, and there you can use the occupancies that's provided by SAN. So if you design an office, then that's 15 square meters per person. That's what we actually define it as. And here you'll see that they've already defined the amount of heat gain for a person to be 90 watts per person. Now, if you're designing a gym, it's going to be higher. And you'll have to go and look at the ASHRAE Fundamentals Handbook does actually provide figures on what the wattage is that a person radiates when they're running, for instance. It's much higher. It's like 150, 170 watts. Again, that must be based on facts you've got. So otherwise, I will just keep those assumptions as they are, 90 and 60. And then again, remember, they're not sitting there in the office all the time. We've defined it as to be there at certain times and not, and you'll put that profile in. If you've done that now, what you'll see is we've now defined that there would be a plug load density from computers, a lighting density from light, and then also the office people. So there's 3 temperature gains, and generally that's what we use. I mean, there can be others if you know specifics, but that's usually the internal gains that you have to be aware of and include in your model. Good. This is the end of the internal gains. We will then next talk about air exchanges.